Yeah, don't do that. All right. We got the noble gas structure, right? Got phosphorus. Here we go. Noble gases have a filled s and p orbital. We didn't actually expect them to be able to be chemically reactive. However, once they get big enough, we have the d orbital space available. And so we spent a bunch of money, and we started playing with krypton and xenon and radon. Okay? So xenon tetrafluoride. Have we made this one? Does xenon tetrafluoride have a dipole moment? No. What's its structure, molecular shape, going to be?
Square.
Good job. This is xenon tetrafluoride, square planar. Right?
Do turn.
Looks like it has legs.
Okay. There we go. We did this, right? We do nitrate?
I think so.
Yeah, we did.
Probably done it a few times.
What are we doing this? We did that one. We finished there. All right. We talked about we did that one. We did methanol. Okay. Talked about the Vesper model, right? Yeah, phosphine.
Oh yeah, we passed that.
We did this, right?
Yep. Passed.
Oh. We ended on a question, that's all I remember.
Yeah, it was the last dive.
There we go. Let's do this. Which of the following statements about the species N2COCN-1, or what's CN-1? Cyanide. NO plus. Which one of these is false? Which one's false? What? Which one of these is false? Which one is false?
I already wrote it down.
Which one do you think? Does each one of these contain a triple bond?
No. Yeah. They do?
Well, yeah, it's not the right answer, though.
No. Because we're asking which one's false, yes? Are they all linear?
Yes.
They're all linear because there are only two, and it's the only choice. Is the bond in every one of these polar?
No.
Which one's? N2 is not polar. Very good.
What did isoelectronic mean?
Oh, because N2.
Same electron configuration. Same number of electrons, same electron configuration. All right.
Can you do what's it called? The thing for CO, please?
Lewis dot structure?
Yeah.
So this is CO, right? Okay, I'm going to go 1, 2, 3, 4. Okay. I'm going to connect these, right? They all need to have 8, right? Yes, okay. So the way we do that, this is what we would normally see, right? I got double. I mean, oxygen's happy, and you normally expect to have oxygen just have a double bond. Okay. The problem is, notice there's no charge here, right? Okay, y'all following me? What we're going to do is we're going to take these two together so they're not lonely. I'm going to take these two and share. And that's carbon monoxide. So now everybody's happy. We actually share. Okay? It's a triple bond. Let's walk through it, sort of the longer version, because that's a question that comes up. So carbon has how many valence electrons? It has 4, and oxygen has 6. So altogether they have 10. So they got 10 electrons. And is there any charge here? No, so that means we got to have 10 electrons, and we got to have an arrangement where everybody's happy with only 10 electrons. So let's go ahead and draw. I'm going to do carbon and oxygen. I'm going to have 10 electrons, and that one line indicates how many? 2. So I'm going to get rid of 2 electrons. That's going to leave me with 8. Okay, so that's 1, 2. I already got those 2. 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. This has the right number of electrons. It has 10 total electrons. Y'all okay with that? Is anybody happy here? No, who's not happy? Oxygen's not happy, so I'm going to get rid of these electrons. All of them, there we go. And so instead of 10 electrons, I'm going to put a double bond here. Now I'm going to get rid of 4, right? That's going to leave me with 4 left. So this has 2, 4, 5, 6. Okay? Is anybody not happy now? Is that the right number of electrons, first of all? 1, 2, 3, 4, 5, 6, 7, 8. All right, so there's mine 9, 10, right? Except I don't need that. This goes over here at 9, 10, because carbon's got its 8 now. Is everybody happy? Nobody happy. Y'all okay? We good here? See what I did? I just took the electrons that were left over and mapped them out.
Okay. But
No, I didn't. There we go. All right, there we go. There we go. That's what I'm supposed to have, right? So 1, 2, 3, 4, and I mapped up 5, 6, 7, 8, right? With 10. No, this is why. Y'all are killing me here. All right, there we go.
We told you like 3 times.
Oh, you did. I didn't hear 6.
rewatch the video.
Rewatch the video. Instant replay. All right, there we go. That's what it's supposed to look like. That was what confused me. All right. So I had 4 here in the bonds, and 1, 2, 3, 4, 5, 6 individual, right? But is everybody happy? No. Who's not happy? Oxygen. All right, so once again, let's get rid of these electrons here. And I'm going to have 10 electrons. I'm going to put another bond here, and minus 6 this time. And now I have 4. And so I'm going to have 1, 2, 3, 4. Now is everybody happy?
Yeah.
Everybody's happy. Everybody has 8, and I've used the right number of electrons. So carbon monoxide has a triple bond. This is unusual for oxygen, but it still exists. And you can see if I'm still looking at, this is a linear, right? Because I only have the 2 atoms. Cool?
The highest you can go is a triple bond.
Yes, the highest you can go is a triple bond, and that has to do with this structure here. You can actually think about this structure here. I can go 1, 2, and 3. There's no way to arrange this where I can get all 4 electrons in the same direction. So 1, 2, 3 triple bonds. And if you remember our overlaps, we had this is going to be 1 sigma and 2 pi bonds. Okay. All right, next question. Approximate measure of the bond angles about the carbon atom in the formaldehyde molecule H2CO. You need to draw the Lewis dot structure for this. Draw that Lewis dot structure. Good? What are those angles going to be? 120. That's exactly right. What type of structure does the XeOF2 molecule have? Good question. We'll stretch your brain just a little bit. What's that?
What's the citron?
Xenon. Good times. Chemistry is fun. Fun is chemistry. The very realization of having fun is, in fact, chemistry. That's no fun. That would be fun, yes. What do we get? We got our structure, first of all. Is that okay? Is that okay? ZE. Yeah, I think you're probably right. Let's do it this way. Let me double bond here. 1, 2, 3, 4, 5, 6. That's right. Okay. That look right? What'd you get? You didn't draw it like that?
Yeah, but I got the right bonds.
Okay. Yeah, let me make it a little prettier. 1, 2, 3, 4, 5, 6, 7, 8. All right. You okay with that? Okay. Is that right? T-shaped? And you don't even have to look at it. You don't even have to have this right. You can just simply count. You know it's going to have a double bond. Right. I'm going to look at this. I think this person gave me the structure wrong. Uh-huh. Interesting. Yeah, it's got the bond wrong. Okay. So I looked it up. It's a single bond here.
What? What? That's not right.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
I still think it's double bond. I got a
There's the 2. There's single bond. Yeah, okay. It was single bond the way I drew it the first time. All right. And then there you go. Okay. That's what it looks like. Either way, still T-shaped, right? Still T-shaped. All right.
Where's the other electron?
They're all here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
What? Wait.
Oh, wait.
1, 2.
So let's count them all up. So xenon had 8, right?
Yes.
Fluorine 7, 7, and 6, right?
Wait, but why couldn't it be double bond? Like, is there a reason for that?
Because an oxygen 28.
Oh,
we have
wait.
too many.
Yeah.
So 28, right? And so there's 7, 7, right? 7, 8. Should be.
But why wouldn't you double bond oxygen? Because
So I think you want to check the, let's look here and see the formal charge. That's the wrong one. There it is.
Quality writing makes
Stop.
your school
No, I said stop. Thank you. So there's a guy who did like his PhD thesis and he has hundreds of, I think it's PhD or master's, one of the two, is like hundreds of YouTube videos on Lewis dot structures. So if you're ever curious, you can look those up. But yeah, that's what it's supposed to look like. And so it's T-shaped. Everybody got T-shaped, right?
And what's his name?
I think it's this guy. I think it's Wayne Breslin. But you can look it up. They're all the same. They're like white background, black text. Videos.
Oh, I think I've seen someone.
Yeah, let's see. He has. Yeah, he's got. Yeah, this is the guy. He's got like.
Who is it? This
That is
I think it's Wayne Breslin.
I don't know, just to double check. I'm like, oh, what's the.
Yeah. Anyway. Which of the following statements best describes BF3 and NF3? There's electron geometry. This is a question somebody asked me in last class about electron arrangement versus molecular. So geometry refers to electron pairs and shape is atom arrangement.
Is this guy his name?
What?
Is this guy his real name?
What is his name? Wayne
Yeah, wait.
Breslin.
Wayne
Breslin. Okay. All right, y'all good here?
Yeah.
All got the answers? Cool. You should be able to answer this. Do they have the same geometry and same shape? They have different geometries but same shape. Different geometries and different shapes. Do they have variable geometry shapes? NF3, BF3. First of all, BF3 is what kind of shape? Trigonal planar. NF3 is,
Well,
right. So the electron is tetrahedral. The molecular shape would be pyramidal. Trigonal pyramidal. Okay? So they don't have the same because BF3 has 3 regions of electron density. NF3 has 4 regions of electron density. Okay? So different geometries, different shapes.
We're done?
Chapter 8 is done. Now we got to work on 9 and 22.5. We're going to fly through 9.
Next one class.
9's pretty small. It's not
9's really small, and it's talking about stuff we're not going to dig into a lot, but we're going to fly through 9.